Hi everyone, today I'm gonna start a new tutorial series on Holland wind model. Basically, this is a parametric wind model. So sometimes we need a wind forcing for any storm surge modeling or for any kind of analysis for a coastal hazard analysis. If you have the wind data, so you can even calculate the risk, right, for any coastal area or for any location. So you have to be able to produce that wind field and the pressure field, because during the storm surge, we have huge, right, wind velocity, and then the pressure drastically drops. So what happens then? The environmental disaster, right? We saw that. So that's why we need to have a model if you want to predict. So people are working on that. If you want to predict the future event, you need to have that predicted data set. So no model can do that except this parametric wind model, because we are going to use equation. That equation generate after taking some input. If you have input data, if you have like a predicted track, that which way the storm may move or may shift, because in reality it drastically changes its right path or the track. We call it track. So if you have the best track, so there are different organizations, they even the National Hurricane Center, ACE-WRF, and then other European Union, they generate that best track and they even publish that data. So if you quickly adapt that data set, and then if you just use that one, if you write, if you can utilize that Holland code, the equation to code, or you can make any software package, you can do that. So what I have done here, I have written code in MATLAB, not MATLAB. Yeah, I have one in MATLAB, so I'll show you the next time. But today I'm going to show you the code I have written in Python with the help of European Union. So they have some kind of codes. So what I did, I just customized that code for my purpose, and I modified some of their script to serve the purpose. And yeah, so out of this model, so we'll have a NetCDF file that will give us the X component of wind and Y component of wind, and at the same time the pressure. So once we have this information, we can even create the input file for our any model, delta T model or any other model. So that's the reason we have to have because that is the most important forcing we need. So what I tried, I just took a very big shot on that one, and it was really difficult for me to generate. Literally, it's a big code, and I have to say that. And let me just share my screen. And yeah, because if you just want to develop any model or any big code, so you have to use at first that Jupyter notebook, and then you can test what it is giving. And then what I did, I just compiled all them together in a single file. I'll show you that, and I'll run that in a Linux machine, and then it will generate all together. So okay, let me just quickly share my screen, and then okay, I'm going to show you what I'm doing here. So I have that first step here. Okay, so I downloaded this data from ATCF. Okay, the link is there. If I click there, so from this one, I can download this data set from ACE-WRF for this link. I already downloaded that one. So yeah, at first, what I'm doing, I'm just asking, okay, I'm putting MATLAB in line right here, and I'm just okay, running this code here, and then I'm importing this operating system, and then NumPy, NetCDF, because I'll write the NetCDF data, and then for copying directory, because all of them are not basically needed here. That for plotting purpose, and because I'll handle this data frame most of the time. That's why I need that Panda data frame. And here I'm assigning the conversion factor from nautical mile to meter, and from knot to nautical mile to, right, this is the wind speed to the meter per second, and then the angular velocity, calculating this, and then the air density assigning as rho, and the radius of the earth, right, we know that. And then from degree to radian or degree to meter, so I'm converting this one. And then the atmospheric pressure, the usual atmospheric pressure, we assume like 101.325 Pascal. And here I'm just dividing that, I'm dividing this way, right? northeast, northwest, southwest, and southeast. This is how wind direction has been assigned, and then the maximum radius of the storm I'm considering 500 kilometer. Okay, and okay, let me just quickly run this one as well. It's done because there is nothing, and here I have the input file inside that directory, and I'm gonna show you what is the name. So this will be the name of the file. Okay, I'm just running this one first, and specifying nothing happened yet. It is just assigning the path, best track, and inside that one I have here is inside this temporary directory, I'm assigning that name. Okay, that name, Florence. And if I open that file, what I have inside that, so I'm basically this AL. If I go to that link, I can download that one, means Atlantic Basin, and this is the number of the basin, this is the date, right, and the source is verb, and then that wind direction, and these are the radius, right? So I'll describe later on, because this file is big, we don't need all of them. So out of this one, we have to do some pre-processing. So that is a kind of difficult thing. You have to basically study a lot of information here, and you can see after assigning this path, and I'm just reading that file, Florence. Okay, that file, text file, and here is in that file you can't see the header. The first one, basin, then it is kind of that number. Okay, and then we have the date time, and this is the tech number, and then they have tech, and then tau, this is the hour, and latitude, either it's north or south, or longitude, and then we have this one, and Vmax, maximum velocity, and then mean sea level pressure. These are the wind code, and this is radius 1, 2, 3, 4 means because for a storm surge, what we did, or for any wind model, what we do, we basically we extract wind speed from 34 nautical mile for 50 nautical mile radius, and then for 64 and 100 to calculate the radial velocity and for other velocities. So we have everything, where the eye is located and subregion, everything. So we don't need that. So these are the header description. You can find it from this source. It is there, right? And then I'm using that, and I'm just parsing. So that's why the first step, I'm dividing it into 4 pieces. The first is the parsing of this data, means pre-processing. I'm running that one. So now header is there, and I'm just now combining the header with the text file I just showed you here, right? The text file is missing the header description. So these are the header. I'm just attaching this header to there, and then here is the next code, and here I'm displaying what I have. See, if I just read that, there is nothing. Okay, and after that, this is the text file I'm reading. I need only that 37 columns, and out of this 37 column, I'm assigning that header. I just prepared ATCF, this header description, ATCF. I'm attaching that one, concatenating. Okay, so that's the header I'm attaching, and then you'll see the header here if I just display. So now you can see the header. Which one is this? This is basin, this is CY, this is the dead time. Okay, these are the description. And then, because there are, see, you can see the tau is repeating, the hour is repeating, tau, 6, 6, 12, 18, this one, sometimes it repeats, see? And I'm taking care of this one, 36, 36, 36. Same time, it is giving 3 different values for different wind direction. So that's why I'm taking care of that one first. I'm saturating, and I'm removing that duplicacy here, and now you can see the single tau. Okay, 0, 6, 12, 18, 6-hour interval, because we have the data for 6-hour interval. And now I'm resetting that index to normal index. This is only the pre-processing, and here I'm just assigning the storm name, because that file is missing the storm name. I'm trying to ask the query, okay, split into these pieces. These are simple, and Florence will be the storm name, and I already assigned that one. Okay, so these are the output I have, and then I'm checking this lat long. We don't need that one here. Okay. And then you need to go through each of these steps. Nothing else. These are the pre-processing. I'm just testing. That's why I'm showing you here. And now I'm checking if it is crossing the international boundary or not. So this is the latitude and longitude. We know the limit. And here it's checking. And finally, I'm displaying the track, right? What is the track? So that is the track. You can see. And then out of that file, I'm extracting the Vmax, mean sea level, and the pressure in millibar, right? And assigning this tau as integer because this is the time hour. We need that as integer. I'm just converting this little pieces, piece by piece. And I'm also assigning this mean sea level and pressure in millibar. And then I'm, watching. These are the processing for writing any module or any code. So that is the step. I already made comment on that. And then I'm just assigning this data string here this way. This is a simple task. If you have idea, right, on data frame, then I'm calculating that date time, as this series, date and time. It will be 6-hour interval. It's just this code. I'm just checking every time I'm creating that one, and then I'm checking, and now I'm checking the columns. You don't need to check all of this, but I'm checking what are the columns I need. Out of this column, I won't use everything. So after checking this one, I'll exclude, and then I'm specifying the wind radius because we need the wind velocity at 34 nautical mile northeast, and then 34 southeast, 34 southwest, and 34 northwest as well. And same for 50 and same for 64. So this is what we need to assign, that wind radial. These are the, I'm creating another empty data frame, and then I'll assign the velocity for these radial distances. So that's the idea. I'm just quickly doing and asking the wind code is that NEQ, and based on that, I'm extracting the value of the wind radius. See here, I'm assigning. I generated the empty data frame, and then from this keyword, it is there in the file. I'm extracting and assigning that, filling up this empty data frame with that value. I have the value, and then I'll calculate, and then I'm resetting the index. I'm attaching that date time. Now I have the new data frame. This is the pre-processing, and then I'm creating another input matrix using that storm name. Now we'll have the storm name. Still, it's Florence. See, you can see I attached the name, storm name here. Previously, it was missing. So I'm just basically preparing the input file, and then I'm still checking and removing the duplicacy, and then if there is anything, all these steps we need. And every time I do something, I just check it. That's why you can see a lot of windows, right? Now, this is the final step. We have time, storm name, we have latitude, longitude. These are the format. We need the center pressure, we need the environmental pressure, we need Rmax, Vmax, and wind velocity at this nautical mile and this direction. We have the complete data frame because using this data frame, we'll use the Holland equation to calculate the wind speed. And I'm taking care of any non-value missing value. And after doing all this thing, I'm again here displaying. If I can't see anything, then if there is anything missing value, I'm specifying if it is -99. This is the general step. If you have idea about that one, then I'm calculating the pressure drop. This is the difference between the environmental pressure and the pressure at the eye of the storm. So you can see how much pressure dropped during this storm or for that specific time period. And we need that because in the equation, we have to assign that one. And then I'm just creating output for the next step. So that is the processing, indexing. I'm testing the date time is okay or not. Then I'm assigning this time as index again. Okay, time is there. It is see 0 days, 0 days 6 hours, 0 days 12 hours, and then 0 days 18 hours, 1 day 0 hours. So it is just increasing. I'm just taking a track, and now I'm that also assigning hourly from 6 hours to 1 hour. Okay, that see we have this one, and here we have 12, 13, 13, 13. This is 13, 6, 13, 12. Still the 6 hour is there, and then I have another level, basically that number level, adding this one. It is basically targeting the specific format. So that's why I'm doing this. These are the pre-processing. That's why sometimes I did a lot of extra steps. And here column, I'm just rearranging this column. So I made this order. It should be this order. I'm checking it, and I'm just rearranging the header because these are in nautical miles. So I'm just converting it to meter per second and this meter, and then making another. So these are the difference, see, from this input to that input. I just converted everything. Ultimately, we need that. And then I'm saving this file. Finally, I wrote one combined code that can do this pretty quickly within one single command. And I'm just taking output, okay, for the next step. It's done. It's there. In the temporary file, it's creating. For step 1, it generated this file. And then it will read this one. And then it will go for the next one. For the next step, we have to go to a step 2. Step 2, and then you can see that I already tested this one. Estimate of translational and Coriolis velocity. So we are just estimating, because of the Earth's rotational speed, storm has a translational speed. We need to calculate that. We have to consider that one as well. So here I'm just doing the same thing, describing the constant and header, because these are the separate file. These are the radial columns I'm assigning, these 64 northeast, southeast. We need that one. And then we have to estimate the Holland parameter. Okay. If you see the Holland equation, it has some parameter called K and B and X. These are the variables we have to estimate. So here I'm going to estimate the Holland parameter using Monte Carlo method. See, I'm just reading the previous input file, and it is this one, nothing else. So if you have, and I'm also assigning, I'm doing same thing over and over here for most of the, because these files are separate. That's why I'm just making it individual file. And yeah, for translational velocity, again, I'm testing, and I'm testing the track if it is okay. So this is the track of that storm Florence. Yeah, if I don't see anything, so I can't even do all of my processing. Okay, so then I'm just assigning the dead time, because it is 6 hours, and I'm just converting it to second. For 6 hours into 6 into 3600, and it will give you this number. And now I need to calculate the velocity. I'm making an array, NumPy array, displaying it, and then calculating this velocity component, X component, Y component of that Coriolis velocity. And from this one, X, Y, I'm just making a resultant velocity here. I'm just printing, these are the printing steps. And then I'm just computing that tangent of unit vector from this tutorial series. This is the processing tangent. I'm taking care of the angles and using this notation, the velocity notation, Vx, Vy, and adding there inside the file. Nothing else. This is pretty complicated. You need a lot of time because it is complete software package, complete software package. It is pretty, yeah, it took a lot of time for me. And now I'm calculating the radius here, the B naught, assume exponential decay, right? In the manual or in the publication, we have that equation. And I'm just displaying this one, because when a storm moves from one place to another place, you have to consider the Coriolis effect, right? That's why we're dividing that 360° into 4 pieces and 4 quadrant basically, and then we're calculating that relative velocity, because the wind, storm wind, it has a circular velocity, and the storm is also moving from one place to another. So that's how we'll have a relative velocity. We're calculating this one, the relative velocity for the storm, and then I'm taking care. Yeah, you have to take care of you have to reverse everything if it is in the southern hemisphere. Then you have to just use minus instead of plus for that velocity. Because we know that in the northern hemisphere, the storm rotates like anti-clockwise, and then in the southern hemisphere, it is clockwise. So that's how we have to take care of that one, right? And I'm just dividing this delta, it's the radius, and nothing else. I'm displaying here. I'm also displaying here, and I'm just going to calculate this Coriolis parameter. This is the equation. F is equal to 2 omega into sine latitude. Then it will calculate that P and CO, and I'm displaying this. I'm calculating each of this for each of this radial velocity, right? And I'm again displaying everything is okay or not. I'm making one single data frame again and checking the time and setting the index, time index 1, 2, 3. The 0, 6. This is the time step we have, because we need to calculate that one. And then I'm taking output as step 2. I'm gonna start step 1 is finished. Then we'll estimate other parameter, Holland parameter using Monte Carlo. Because we don't know, these are the variables. We have 3 variables, K, B, and X. We need to estimate that one using random variable, okay? I'm just using the same header and radial column, testing everything is okay or not. I haven't started yet. And this is the function that calculates that is the Holland function for velocity, okay? Yeah, writing that function. And see, reading from step 2, I saved that value. It is just displaying if it is okay. It's accurately importing. And then I'm just selecting one time step. It is I or IT is equal to 20. I'm calculating for one time step. And then if it is okay, then I'll calculate for all. And then I'll display the wind SWAT. I'm calculating for one time step, and then I'll repeat that. So that's why using Monte Carlo, I'm using a 10,000 random variable, okay? Random number as a sample to calculate that. I'm calculating the statistics and yeah, the pressure drop, everything, Rmax, everything, and then I'm plotting. If I can't see, I even can't understand. So this is the plot. It is going to plot. This is the wind field for time step 1. This is this I, and you can see the velocity. See, not in the I, just from I to a certain distance, the velocity is maximum. And if it go away, right, to the radial direction, the velocity is less. And then I have more plot, but I'm generating that one. And for all time steps, I've written one basically function with the help of that European Union, because they have this format, and then I'm creating empty data frame and empty dictionary basically, and then adding to the main file, checking the shape. I have 54, so I have to remove this empty row. The next step will do that here, and then I'm writing that input right for the next step. So the next step will be the final one. I'm just testing if it is okay or not. Just reformatting everything, okay, and then trying to yeah, if it is showing error, no problem. Now we are saving this data for third step. And if you want to see the difference, dp and dph, these are the changes. See, it's showing maximum and maximum velocity at h. Okay, and then the final one, the final step, it is just going to read the previous file. And again, I'm just defining the same file, because these are the separate one, reading from step 3. The name is step 3, and checking if it is okay or not. Yeah, I have header description, everything. See, I need that B parameter. That's why I'm just estimating. I already estimated that one B parameter for each time step, and then K. We need that. And we also have other velocity from our observation based track. And then, yeah, I'm assigning again that index. It is basically changing index from dead time to normal one. And then I'm just plotting if it is okay or not, using linear interpolation, and now using cubical. And then from lat long, I'm going to start the main calculation. I'm just writing this Holland equation as a function. So that will be calculating for one time step. Again, see, for one time step, I'm checking and plotting using that function I wrote, right? And here it is, 1D Holland function, means it will show you the comparison of velocity. See, this is the ratio and this is the velocity. If you, this is the I, from I, if you go to a certain distance, it will be higher than this one. Since it is a ratio, it is giving you the ratio with the total radius with the radius at a certain location. So that's the difference. And then if you want to see the spatial plot, how it looks like this one. At the center, we have this minimum pressure, right? That's why the velocity is less. This is the velocity profile, spatial distribution of velocity. Since it is a parametric model, you can see it is kind of circle. But one thing you should see here, observe that the velocity, this yellow color is the higher one, right? So on the right side, it will be on higher velocity will be on the right side of the storm because the rotation is this way. That's why it is the phenomena of storm that happened in the northern hemisphere. If it is in the southern hemisphere, the rotation will be this way, then velocity will be here higher. So the equation can take care of that one. That is good. And then we're computing for all time steps. And you will see for all time steps. I'm just checking, and yeah, I'm just exporting. So that is the bigger picture, big picture. You can see I is there and the wind field. It is basically this one. And if I run this code, it will calculate the, yeah, it calculated for each time step. And here it is showing the, this is the radius, right? Radius, and it is the velocity. And for each time step, if I move, it is moving. See, the storm is moving from this to that. I'm just going back, it's taking time, and see if I move forward, yeah, it is starting, and this is the land. Here we have the land. We have like 53 time steps. See, the storm is moving this way. See, velocity is increasing before landfall. So now, yeah, now landfall happens. That's why the velocity is pretty big. These are in meter per second. If you convert it to nautical mile or kilometer per hour, it will be more than 100 kilometers per hour. And now what I need to do, I need to calculate for every time step. So started here, and it is just following the track and showing the right velocity field. This is called SWOT. And now I'm testing if it is okay. Then I'm going to interpolate for 5 minutes. I need the output wind speed for 5 minutes, or you can even make the output for 30 minutes, whatever it is. Okay, let me just make 30 minutes. Okay, it will make 30 minutes, and then it will use linear interpolation, and it will create this data frame for 30 minutes. And then I'm checking the values if it is okay. Time values, it is creating for 30 minutes. See, 30 minutes, 30 minutes, 30 minutes. Okay, it's okay. And then I'm checking. We can see this date, September 4, 18, hour 30, and then 19, 30, 20, 30 minutes. It calculated that one. And I'm checking all of this number. So these are the time step, because I'm gonna write a NetCDF file. So that's why I'm extracting this UX, UI, and PP. So I'm writing this empty list using that array, and then see it is taking time. It is running because I have huge data and it's already done. I'm making this NumPy array, and then I'm calculating that velocity, resultant velocity. And then last time I'm showing this SWOT for half an hour. This was for 6-hour interval. That's why it is this. And after interpolating, it is more sharper than that one. And I'm just gonna save that U, V, and P component of the wind as this NetCDF file, okay? This NetCDF file. It generated empty NetCDF file, and then it's going to write that one, okay? So that's that. I'm checking the time and everything is okay. Now this command will write. It's done. See, it's done. How many time steps I have? This time step. So it's there. It's already written, okay? This UVC, this one. This file, it has written. Okay, let me check if I can show you this one. If I just, it is this file. If I upload this file in my Linux machine, then I can maybe quickly show you what it is giving us, because I already maybe I have that. Yeah, it's there. Yeah, I can upload it here. Okay, I can upload it pretty quickly, and I can show you the variables UVC. So I need to go back one step, and then I think hopefully I'll have that UVC. Okay. So what is the command? The command for that one, ncl _ file dump, and then uv, name of the file is already there. It will show you the variable. Okay. So I have the file here. I have the file. It has this number of latitude 100, 100, and time step is 3637. Right. You can see that I checked it. This number of time we have, and then these are the latitude and U component. If you assign time, latitude, longitude, it will give you that. So from this one, I'm using another code to extract that value. I'll show you in the next tutorial how to do that. And pressure, it has U, V, and pressure. Okay. So from this file, we can even generate the the animation of that storm. And I already made it. I can even show you that one if you want. I think it's there. Yeah, maybe it's there. Okay. I created that animation for 6-hour interval, that pressure, using that script here. See, storm is started from here, and then it is still in the Atlantic Ocean. That's why the radius is pretty small and it is not that strong. It is moving to the land. See, it started, it's big, and now landfall happened, and it still is moving this way, following that track. So that is the storm we have. So we created the wind field for this storm. And if I want to show you the wind field, maybe it is going to take a little bit time. Yeah, let me wind. Yeah. And we also have that is the wind field. It will show you. That is the wind field. It's changing. See, at the center of the wind, the center of the storm, this is the eye. We have less because it is empty. There is no that much wind. But see, from that center to a certain distance, we have hues. And and on the right side, you can see that the wind speed is pretty big. That's the assumption we have, and it is increasing. It is increasing before landfall. It is shifting. See, the coordinate is shifting. I'm just zooming in. See, the eye is increasing, and the wind speed is so big and so huge, and landfall occurred. Okay, and repeated. And that's why I just plotted another wind profile, how the wind velocity just changes if you just move from eye of the storm to the radial direction. So that is this is the radial direction from the eye, and we have peak here at a certain distance from the eye, and see, it is changing. When a storm is just moving to the land, the velocity is changing. The maximum velocity, still the velocity profile is same. I'm just checking if it is consistent when it moves, because in reality, this should be this way. So that's why we have to check everything. If everything is okay, then I can create, because I already have that NetCDF file, right? That NC file, and from that NetCDF file, I can even generate that space varying wind and pressure, and then I can input that value in my in my model. So in the next tutorial, what I'll show how to extract data from this NetCDF file, and then I'll show you how to plot this one and validate. I'll validate this model with observation, and before that, I also have compile all this together, right? So that's what I was trying to show you that. Okay, maybe here it is, or okay, where I put it, maybe in the other, maybe here, right? Or where? Okay, let me just check. There, maybe there. Where's the Holland model I just displayed, right? Maybe it's here. Okay, I have to go back. Yeah, do we have Holland model here? Maybe, oh no, it's not here, because it should be in different, server. Okay, let me just quickly go back to that Holland model, and I can definitely, if it is, yeah, it should be here, and I have that Holland model. Here it is, okay? And then Holland model, okay? Not output. Oh, I have to go to script. I have the Holland model. So if I run one, so what I did, I just compiled the whole 4 step here. See, it's pretty big code, and it's there. It's 687 pitch, and finally it is writing this one as a NetCDF file, okay? NetCDF file, it will write the name of the NetCDF file will be this one, Florence Holland wind XY6 or NetCDF 4. If I run that one, it will quickly show you that. Okay, Holland model, and then Florence, okay, BTK, and 6 hour. If I run it, yeah, it is going to run pretty quickly. See, it is just, since it is a Linux machine, it is displaying everything at the same time. It is calculating, and even it will, yeah, show you that wind plot. If I gonna share my screen, share my screen on the other side, you'll see it is plotting at the same time. The same plot I'm displaying here on the other window. It is going to show you everything, literally everything. See, it's taking time plotting the wind distribution. It is taking time for the calculation. All that step we did there, it is just doing everything within 2 minutes. But writing the entire code, it took a lot of time to process and test, because I had to test multiple times using different data set, and the formatting is very important as well. Then after doing all this processing, you can do your final job. So that's why what I'm trying to do, I'm trying to just improve the model performance, and next time, yeah, I'll make another tutorial maybe how to validate this wind model, this parametric wind model, how to extract data from this wind model, because I'll assign, because I have some observation, like 50, 60 observation point, and then I'll extract data from that for that locations, and then I'll compare again, I'll calculate the statistics. And then what I did, I just did the same thing. I just extracted the source code from Delft3D, right? Delft3D dashboard. They have the source code written in MATLAB. So I also reproduced that one and compared with my model. So if these two are okay, then my model is even, because they calculated this thing separately, and I'm calculating this one in a different way. In Python, they calculated this one in MATLAB. They estimated the model parameter separately. I'm estimating the model parameter using Monte Carlo, right? So these are the differences. So if the results and the objective, these are same, then it's okay, right? Then it's okay to use this model or that model. Because sometimes This is useful, sometimes that is useful. So we can do that. So the calculation is going on. It is plotting the wind distribution. It is showing the message here, but I think it is going to take a while to display. Shortly, you will see the wind distribution, because it is taking a while. Maybe the server is busy. Other people, maybe they're just occupying all these processors, but I'm using only one. Still, maybe it is in a queue, but I don't think so. It should work, but the calculation is so huge. That's why it is taking a while to plot and calculate and plot, because it is a two-dimensional plot. It is plotting the entire Atlantic Ocean and calculating because the resolution I used here is pretty high resolution, other than the resolution I used there. I just extracted see, it's there. See, the storm is 500, means 1,000 kilometers diameter. This is the SWOT. It just displayed. It just showed, right? You just saw. It just displayed that one. And again, it is calculating. It's trying to calculate for all time step. You just saw for one time step, and then it's interpolating for 5 minutes or for 1 hour. I can't remember. Yeah, maybe it's for 1 hour, and then it will show you one more time before writing that NetCDF file. So that is the idea. You can develop a code using that Jupyter notebook, and you can see step by step. And then you can, if your code is okay after testing, then you can use that in your Linux machine, and it will do the performance. Yeah, it will do the job for it. And performance is really good if you run the code in Linux machine, because it has a very big RAM, and yeah, storage is okay. The processor speed is also okay. If you have access to that, you can use this HPC. Otherwise, you can do the same job using your Windows machine, or even using your Ubuntu. Everything will be okay, but maybe it will take a while for doing all this processing on Windows or Ubuntu or in any local machine. But here it is not taking that much time. See, the same thing I just demonstrated for half an hour. It is doing the same job for within 5 minutes. That's the last image you saw, right? And yeah, it's written already. It finished that process. See, it finished. And Holland model output. If I go to the previous directory, Holland model output, and it generated this one. See the date, you can see the date time. This is now, right? 17th of August 2021 at 8:46. So this file is generated, and yeah, it's already even saved this distribution, velocity, all this. Yeah, it saved the wind profile as well. It saved this, and SWOT. This is the previous one, 3 hour, but I'm writing this 6 hour right now, this one. Okay, so that's that. So I'm gonna finish this now, and then next tutorial I'll show you how to extract data from this one and how to validate. Yeah, I'll test this model performance, because this is very important. Any storm surge model needs very accurate wind field. So thank you very much for, and yeah, welcome to the new tutorial series. Here I'll upload this one as well, and if you have any query, any comment, you can mention that one. I'll appreciate that. Okay, so thanks again.